Hi, in this video we're going to look at the level 1 science standard, that is the Physics, Earth and Space Science standard of Demonstrate Understanding of Physical Systems using Energy Concepts. That's Achievement Standard 92027 of level 1 NCEA. Okay, so we can see here that on the first page of the exam booklet we've got it's telling us it's 5 credits, which each of the standards are at level 1. Instructions here that you should do all of the questions, show all working, and if you need extra space, use the back of the booklet. Don't write on the side area. And okay, let's get into it. Question 1, energy changes. Janet drops a tennis ball from the top of a building. Okay, so what type of energy changes will take place as the ball falls down? Well, obviously when the ball is on top of the building, it has gravitational potential energy, because it could fall off and go all the way down to the ground. As it's falling, of course, it's turning that gravitational potential energy into kinetic energy. So the energy changes that happen here, we're going to write gravitational potential energy and then push an arrow and put kinetic energy on the other side. That's the transformation that's happened. Make sure the arrow is pointing towards the kinetic energy from the gravitational potential energy. Now that is an achieved point for that point there, and we're going to count up the total number of achieved merit and excellence points, and those will determine what number grade we get for each question out of 8. Okay, so part B, the mass of the tennis ball is 0.058 kilograms. Okay, so hey, when we see this data here, what I always like to do is just highlight it, and then I'm going to associate and give its actual quantity that it is. It's a mass, and here's the value. So I'm going to scan this because I'm going to use this later. I'm pretty sure each of these bits of data we're going to use in the question. The tennis ball falls through a height of 14.7 meters. Okay, that's quite a high building. I guess if we take about 3 meters for each story, that's going to be about 4 stories, maybe 5 stories high. Okay, so the height here is 14.7 meters. Show that the gravitational potential energy the ball loses as it falls is 8.6 joules. Okay, so that means they've given us the answer. It's 8.6 joules, but they want to find out the potential energy, the gravitational potential energy. So we go to our resource sheet and we find the equation that has height, mass, potential energy. It's also going to have the other bit of data we might use is a g, the acceleration due to gravity, which is 10. So we know that it's going to be this. The answer is going to be 8.6. But because this is a show answer, we have to be really careful here that we give the equation, we substitute the values in, and then we give the answer. Just working out the answer and writing that down is not going to give us a grade because they've already told us the answer. So we want to find the gravitational potential energy. We find that equation, we write it down, we substitute our values in, mg, remember that was 10 from our resource sheet, and height 14.7, and then we calculate that just to check that we've done everything correct, and of course we come out with the correct answer. The potential energy equals 8.6 joules. Now because this is just one step and it is a show question, we've got an achieved here. But remember, they want us to have the correct, need to show the formula to do this. And there's a reminder in the marking schedule, don't just give someone the correct, the achieved point for the answer here, because there are work that needed to be done. Okay, calculate the speed at which the ball hits the ground. Okay, so this is more difficult, because what we have to first do is make an assumption here. And the assumption is that all of the potential energy has changed into kinetic energy, right? None of it has been lost as friction. So, and we need to calculate the speed. So because potential energy turned into kinetic energy, we can use the kinetic energy equation, EK equals half mv squared. And remember, we made that assumption. I might write that assumption down. So here, and then I substitute the values in. 8.6 is the energy of the kinetic energy. The mass is from up here, 0.0585, and then we have velocity squared, which is velocity is our unknown. Okay, I then solve this or simplify it, and I get 8.6 equals 0.05 0.02925 times v squared. And I'm going to remove this term 0.0925 to the other side, and I do that by dividing both sides by 0.0925. And if I do that, I get v squared equals 8.6 divided by 0.2925. Okay, and the answer to v squared is 294. But now, because I know that v squared equals 294, what I have to do to both sides to find out what v is I have to square root both sides. And when I square root both sides, I get my answer. And so here, square rooting, I've square rooted v already. I'm going to square root 294, and my answer is velocity equals 17.1 meters per second. Now, I need to get the correct answer to, so if I put the correct formula down, plus I put the numbers in and calculate it, but I forgot to square root it at the end, or I forgot to square it. If that was one of my mistakes, I get it achieved. If I get the whole answer correct, I get a merit. So there we go. First page, we have a chance for 3 achieved and 1 merit point. Let's go to the next page. Okay, in reality, the speed of the ball when it hits the ground is not the same as it was calculated in part C. Explain the reason for the difference, including a statement whether the speed was more or less than was calculated. So, of course, we assumed when we did our calculation that all of the potential energy transferred into kinetic energy, but we know as the ball falls through the air, the particles of air will rub against the surface of the ball, and the friction from that will release heat energy. So some of the energy that is being transformed is not transforming into kinetic energy, but it's transforming into heat energy. So the first statement we could write down here is the speed will be less than calculated above. Okay, that's right. And this is because some of the energy would be converted to heat energy due to friction of the particles hitting the surface of the ball. Very specific here. If I want to get an E point for this, I'm going to have to say that it's because the heat energy, because it was converted to heat energy due to friction. So we need to explain that it was a friction between the air particles and the surface, and that produces heat energy. We just can't take a shortcut here and say, oh, it's because of friction or it's because of heat energy. I need a full explanation. So I'll get an achieved here if we said the speed was less, or we said that they lost some energy due to air resistance. A merit if the speed will be less and some energy is lost due to air resistance, friction, drag, heat, whatever. Excellence if we can write the statement correct, right? So if I'd said, okay, it's less because we lost some due to heat energy, merit. But if I said actually lost it due to heat energy because the friction of the particles will transform some of the energy into heat, that's where I get my excellence. Okay, C. Janet's friend Maya retrieves a ball from the ground and runs up 2 flights of stairs covering a total height of 15 meters. Maya has a mass of 48 kilograms and she takes 34.2 seconds to reach the top. Calculate the power. Begin your answer by describing the meaning of power and how it relates to Maya running up the stairs. Stating the assumptions you made, include a unit with your answer. Okay, let's identify the data they've given us. So 15 meters here, that's the distance or height, D equals 15 meters. We have a mass here of 48 kilograms and we have a time of 34.2 seconds. Now, begin your answer by describing the meaning of power. So power is a measure of how much work is done, or the amount of energy that's being used or produced in a given amount of time or in a specific time. So the first thing that we should actually state here is power is how quickly work is done or spent or changed. So quickly refers to time. I could write this down as power is how much is a measure of how much energy is used in a given amount of time as well. That would be another way to explain power. So I've put the equation here. This is what it means. Power equals energy divided by time. When Maya runs up the stairs, her kinetic energy is changed into gravitational potential energy. So the energy that she has from her movement that she's constantly producing from her muscles are producing the kinetic energy that then are turning into potential energy. Assuming all of the kinetic energy is changed to gravitational potential energy and we have no loss from friction, okay, so assuming that, we can say that the EP equals mgh. We can work out the potential energy. The potential energy is equal to her mass, 48, times the acceleration due to gravity, 10, times the height, 15 meters, and we can work out the total amount of potential energy that she gained going to the top, okay? But they want us to calculate the power. So we've calculated the energy, which is actually, we're assuming that that energy that she has gained from potential energy is the same as all of the energy that she has produced from her muscles to formed kinetic energy from that. So we're going to just put this number into the top of the power equation, and we'll go out and substitute the time into the bottom of this power equation, and we get the following, and then we get our answer: power equals 210 watts. Now, if here we said the power is how quickly work is done, or energy is gained or lost, or how much energy per unit of time we get achieved, or we could have said the kinetic energy is changed to gravitational energy, or I mean, I guess you could have said, hey, the chemical potential energy in the muscle was changed to kinetic to gravitational potential energy. Or if we got a correct answer for the first bit, or if we did the calculation correctly for the power but had the wrong numbers, any of those things will give us an achieved grade. We get a merit if we can say that we can explain what power is and that kinetic energy is changed into potential energy, right? So we say that she is changing the kinetic energy produced from her muscles into potential energy. They give us a merit point. We actually get another merit point if we can calculate the potential energy and we can calculate the power. So if we can get both of these calculations correct, we can get an merit point. So there are two opportunities for merit points. That is these first two explanations here, or these two calculations here. Excellence, for the excellence, when the definition of power and connection between kinetic energy and gravitational potential energy, and assume that all kinetic energy is transformed. Okay, so this last bit, that the kinetic energy is, there's no loss through friction, right? So we can only work out her power if we're assuming that she hasn't lost some of the energy she's produced through friction along the way. Otherwise, of course, she would be more powerful than what we worked out, because we're just working out how much she converted into potential energy. So that's the last point. We get all of that down. That's excellence. And if you look on the left here, this is how they mark this whole question. If you've got 2 excellence points, they give you an E8. If you've got 1 excellence and 1 merit point from another place, so if you've got the excellence from here on the left, so sorry, excellence from up here, but you got a merit from here, you can get an E7. If you get 3 merits, you get an M6, 2 merits an M2, and 4, 3, 2, and 1 A's give you an A4, A3, N2, and N1. Okay, let's pop on to the next question. Okay, so this question is called thermal energy. Oliver wants to be able to keep his water cool the whole day while he's at school. Firstly, he tries freezing a bottle of water to take to school. Over day, Oliver finds that it takes a long time for the ice to melt. Once the ice is melted, the water gets to room temperature quite quickly. So what he's saying here is that it takes a long time for all the ice to melt, but as soon as it's melted, it gets warm quite quickly. Okay, so they've given us 3 values here. We've got the specific heat capacity of water, the latent heat of fusion, and the mass of water in the bottle. Now, the latent heat of fusion is L here, and I've just written this out again, and I've written out the mass. Now, what does latent heat of fusion mean? It's the energy required to break the bonds between the particles when we change it from a solid to a liquid. So that's what latent heat is, the amount of energy required to change the state from solid to liquid. But remember, we're breaking the bonds between the particles without the change in the temperature. So it happens So this latent heat of fusion happens at 0 degrees Celsius. It happens, and the temperature of the water will not heat up until all of the solid water, the ice, has been melted. Okay, so here they wanted you to say it's the energy required to change it from solid to a liquid, but they give you a merit here if you said if it's at a constant temperature. In this case, it's at 0 degrees, right? So you could have written that as well. Calculate the heat energy required for 0.075 kilograms of water to change state from solid to liquid. Okay, so the energy here equals the mass times the latent heat. So we know we want to find out the energy, but we know that the mass is 0.75 grams, and we know the latent heat is 334,000. So we just put our formula in here. We get that from our resource sheet. We substitute in the values, and then we get the answer. And the answer here is 250,500 joules. So that's an achieved here for the correct answer. We can accept that, yeah. So that's just an achieved for that. Let's go to the next question. The temperature gains time. The temperature against time graph is shown. Shows us what happens to the ice when it's taken out of the freezer. Use the information provided opposite and the graph to describe the reason why it takes a longer time for the ice to completely melt and a much shorter time for the melted water to get to room temperature. Okay, so here what we're going to do is say that the specific heat capacity of water we can see is 4,200, with the latent heat of fusion is 334,000. So the specific heat capacity of water is how much energy it takes to raise a kilogram of water 1 degree Celsius, right? But so even if we raised it 100 degrees Celsius, we would still only get to, what would that be? 100 times this would be 420,000. Yeah, so that'd be similar. So the specific heat capacity of water is much less than the latent heat of fusion because the energy required to get particles moving faster is less than the energy required to change the state. Yeah, so it takes more energy to change the state than to change the temperature from 0 to 20. Now it's a relative comparison here because it would depend on how much we are increasing the temperature. If we increased it 100, then it would take more energy to it would take more energy to increase the temperature than it would to melt. But in this case, we're just saying, well, how much energy would it take to get to 20 degrees, about the temperature outside, right? And it takes a lot less time because it takes a lot less, because the heat capacity, specific heat capacity of water is a lot less than the latent heat. Now we could carry out a calculation here for both of these. We could put and show this, but in this case, we just, if you can state that the heat, specific heat is much less than latent heat, you get an achieved. If you can say why, because it's just moving the particles instead of breaking bonds, then they give you a merit. Okay, let's go on to the next question. Next question. Oliver can then decides to try using a thermos that holds the same volume of water as his earlier bottle. The thermos flask is also known as a vacuum flask. It is a double-walled glass vessel that is designed to minimize the transfer of heat by keeping hot things hot and cold things cold. Describe two features of the thermos that reduces heat transfer, and explain the type of heat transfer each feature is designed to reduce. Now remember the three types of heat transfer we're looking at, that is radiation, convection, and conduction. Now we can see that there is a vacuum around here, there is a reflective coating on the inside, and there is a stopper on the top. So in this case we can see the vacuum. So the vacuum here, that is the space with no matter, no particles between the inner layer and the outside layer, will stop conduction. Okay, so it's going to stop the particles hitting each other and transferring that kinetic energy, right? So that kinetic energy from particles. Reflective coating here. Reflective coating is usually a silver coating, and what that stops is that stops the loss of infrared radiation, heat radiation. So reflective coating reduces the heat loss via radiation. So remember, it is important that you say that it's electromagnetic radiation. Okay, we could go on and say some of the other things. The stopper, if we put the stopper on top, it will prevent the particles that are hot from rising out, and that would be convection, right? So it will stop that movement. It will also stop conduction of the hot particles at the top bumping into the the cool particles in the air. And it will stop them from moving via particle motion, right? Glass is used as the inside material and the outside material because it's a poor conductor of heat. We could say that as well. So we've got quite a few different things, but we just need, for one, if we can, one feature with descriptions, the correct type of heat transfer, that's achieved. If we have two, that is a merit. If we have two features plus one explanation of the nature of this heat loss. So when we're talking about the nature of the heat loss, we're saying, okay, the reflective coating reduces heat loss via radiation of electromagnetic radiation, right? Or it's just giving a bit more detail to this. Okay, so that would be our excellence. So Oliver decides to test the thermos and finds at the start of the day the temperature of the water is 5 degrees Celsius. 5 hours later, he finds the temperature is 12. Show that the average rate of thermal energy absorption of the water of the thermos over 5 hours is 12 watts. Okay, so if we're using that, if we've got this watts here, we know we're going to be calculating the work. Okay, that is the energy per time period. We have two temperatures here. It started at 5 and it went to 12, so we can find a change in temperature, and the change in temperature is going to be the first part of our calculation. We remember that he said that this thermos holds the same amount of liquid, so its mass is 0.750, and we also know the heat capacity of water from the previous page from our table is 420 joules per kilogram per degree Celsius. So the rate of thermal energy gain can be calculated by using the total energy gain divided by the time taken. What does that mean? That means the rate is the work equals energy over time. But anyway, in order to do that, the first thing we need to do is find out what the change in temperature is, and that is 7 degrees. After we've done that, we can find out how much energy how much energy is lost, and we can work out how much energy is lost by taking the mass of the water that we have here, taking the heat capacity of water, that is how much heat is needed to raise a kilogram of water by 1 degree Celsius. That's this value here, 420 joules. Sorry, 4,200 joules, and we're going to multiply that by the change in temperature. So we chuck those values in here, and we get an answer of 22,050 joules. Okay, so that's how much energy would be gained if it went from 5 to 12 degrees Celsius. Okay, but what is the power, or what is the can we show that the power, the rate of energy loss, that's the power, or the work equals the energy, sorry, the power is the energy over the time. So we chuck the value of power in the top, sorry, the energy in the top, and we put the time in the bottom. Now the time is, they've told us up here it's 5 hours later. So 5 hours, time has to be in a standard unit called seconds. So we know that in every hour there are 60 minutes, and every minute there are 60 seconds. So the time on the bottom is 5 times 60 times 60 to convert hours into seconds. and we get an answer of power equals 1.225 watts, or if we round it to two significant figures, is 1.2 watts, which is exactly what we had at the top. So we get an achieved if we what do we have to do here? Correctly change in room temperature is achieved. Okay, if you worked out with 7 degrees, or we're tempted to use a formula, then you get an achieved. If you get the correct value for the amount of energy gained, which is 22,050, you get a merit, or the correct power using the wrong value of E. So if you got this E value wrong, but you put the correct stuff in the power equation, you can get a merit as well. You get an excellence if you get the correct value at the end, and you can show that that's the same as what you already had. Okay, so that's the end of question 2. And again, question 2 is 2 E's you get an E8, 1 E is an E7, 3 M's an M6, 2 M's an M5, 4, 3, 2, and 1 A's are A4, A3, N2, and N1. Let's look at the last question. Okay, so the last question here is called electricity. So Tane is studying the relationship between current, voltage, and resistance. He uses a power supply, a variable resistor. Doesn't look like a variable resistor, but this, variable resistor here, right, and a piece of resistance wire in a beaker of water. He connects the components as following. Okay, so A, in the energy above diagram, include an ammeter to measure this. So they want us to put an ammeter and a voltmeter into the circuit. So ammeter goes here in series in the circuit, and voltmeter goes across. I want to work the voltage of this wire, so I put the voltmeter across the wire. Now they're going to give us an achieved if we put one of these in the correct place, and a merit if we have both of them. The following graph shows us the relationship between voltage and current. It's showing Ohm's law here. Using information from the graph, calculate the resistance of the coil and include an appropriate unit. Okay, so we want to find resistance. We're going to use Ohm's law here. So V equals IR is Ohm's law. We find that from our resource sheet. We're going to have to rearrange this and find out what R is. So R, we divide both sides by I, and we get R equals V over I. So let's take the voltage. I'll take the biggest voltage here, the change in voltage. So the voltage is 5.6 divided by 0.7. Okay, 5.6 over 0.7 gives me the answer of 8 ohms, and that is the resistance of this resistor. Now give a reason why the wire is submerged in water during the experiment. So because this is a resistance wire, as the electricity goes through, it will heat up this wire. If the wire wasn't in water, it wouldn't be able to transfer its heat quick enough to the air, and it would keep heating up until the wire melted. So the water acts as a way to keep it cool. Okay, so it's somewhere for the heat to be transferred to. And if you can write something about that down, they'll give you an achieved grade. So to get the achieved, you could say, hey, it's keeping it cooler. Keeping temperature constant, and a merit is also keeping temperature of the coil cooler. Okay. If we go to part D here, using the data from the graph, what is the maximum rate of electrical potential energy being used? Okay, so if we have, or we need to find out what the rate of electrical potential energy is here, and the rate of electrical potential energy is just called power, and power equals voltage times current. So we want to find out what is the maximum voltage and current to give us the maximum power. And if we look at this graph, then obviously the maximum voltage we get to on this graph is 5.6, and the maximum current is 0.7. So we go 5.6 times 0.7, and the answer we get is 3.92 watts. That is the maximum power that we get. This question is actually achieved, merit, and excellence for getting the correct answer, which seems I mean, question C and question D seem very generous for this electricity one. Anyway, let's go on and look at the next question. Okay, so one of the components in the circuit is a variable resistor. I've drawn the circuit again at the bottom here. Explain how the variable resistor is used and analyze the effect it has on both the current and the voltage for the components in the circuit as the resistance is increased. Okay, so what happens if we increase the resistance across here to this component, which is the resistor wire that's in the water, and also to the current? Okay, now the total voltage that's produced in this circuit is constant, and it's what's produced by this power source here. Depending on the resistance of each of these components, the variable resistor on the left and the resisting wire on the bottom, they will use a proportion of the voltage equal to their proportion of their resistance. So if the resistor here, the variable resistor, is smaller than the resistance of the wire, it will use a smaller proportion of the voltage. So as we increase the resistance on the variable resistance, it gets a larger share of the voltage. What also happens, if we increase the total resistance of the circuit, then we make it harder for the current to move around the circuit. We reduce the current. So here's what we can say. We can say the following. The variable resistor is used to adjust the total resistance of the circuit to cause the current of the circuit to change. Okay, so it can, remember, if we increase the resistance, we decrease the current. We reduce the resistance, we increase the current. As the resistance increases, the current will decrease. The circuit voltage is not changing. And remember, we can also state here that if we increase the resistance on the resistor here, it gets a larger proportion of the voltage. Now, if you got an achieved here if you were able to say that this variable resistor changes the total resistance of the circuit, or you say that it reduces the current in the circuit, or that it will change the voltage across the coil, because remember, it will change the share of who gets the voltage, the wire or the variable resistor. You get a merit if you said as the resistor increases, the voltage across the coil decreases. Remember, if we increase this resistance on the left, it gets a bigger proportion of the voltage, so therefore the wire gets a smaller proportion. Or you said the total voltage of the circuit stays the same. Excellent. The resistance, the variable resistor increases, the voltage across the coil decreases, and the total current reduces. Okay, so if you put both points down there, you're going to get your excellence. This is quite a tricky concept here, but if you can get the idea that if you increase the voltage, that you reduce the current, that's cool. But you also need to know that if one component increases its resistance, if you increase the resistance here, you reduce the current. If one component increases its resistance, it takes a bigger share of the voltage that's produced by the power supply. So you can get an achieved, a merit, or an excellence here. So if you add up all of the grades that you got for this part of the paper, again, with 2 E's, you get an E8, 1E, 1M, an E7, 3 M's, an M6, 2 M's, an M5. A4, if you've got a 4, 3, 2, or 1, you get an A4, A3, N1, N2. And for the whole paper, if you got 0 to 7 points, you didn't pass. But if you got 8 to 13, you achieved, 14 to 18 merit, and 19 to 24, you got excellence. Hopefully this video here has helped you and given you some confidence with the exam that you might have to sit later on in the year. Hey, I've done another video here for level 1 for the chemistry materials paper, so have a look at that if you need to, and just look out for other videos I might put up.